Good afternoon, class. In today's video, what I'd like to do is to continue our example problems from the section on gas laws by dealing today with the ideal gas law, which is PV equals nRT. If you want to follow along in the from the homework set, this is actually going to be problem number 1 in the homework. So here we go. We've got pressure is 76 newtons per square meter, which in this case I've decided to change it to pascals, and you'll see why when we deal with our gas constant, because our gas constant has kilopascals. So I wanted to just make sure that instead of writing newtons per square meter, which is exactly the same as a pascal, that I actually have it written as pascals, so it's a little bit easier to see where the transition comes in when we talk about our units of pressure. So then we have a volume of 1 cubic meter. Our number of moles is 234 moles. Our gas constant of 8.314 cubic meters times kilopascal divided by moles Kelvin. And of course, why do I have these parentheses, you ask? That is a good question, and I thought I'd address that because when I gave the assignment has to be, it cannot be written, I can't write the unit looking like this in the assignment because it's being typed. So unfortunately I have to write it horizontally, so that I have this fraction bar over here that makes it look like so everything is written in one line instead of broken up onto 2 lines. Now, why is that important? Because if I didn't put this parentheses here, the unit here would look like meters cubed times kilopascals divided by moles, but that times Kelvin might be a little bit harder to tell. Is it meters cubed over kilopascals per mole as one fraction times Kelvin, or is the Kelvin in the denominator? Because if I multiplied this fraction by Kelvin, Kelvin now becomes the numerator of that. So there can be some confusion as to where that unit is placed. But if I put it in parentheses, this is guaranteed to be in the denominator, both of them. Everything in the parentheses is in the denominator. So that's why I wrote it like that, just so that when you see it in the assignment itself, it's not so shocking, like, oh, that's why it's there and that's why you're dealing with it. And of course, if you write it out this way when you're actually doing the work, well, that's fine. They're both totally legitimate ways of looking at the problem, because the work is the same. So let us now actually solve this problem out. So we're going to substitute our given values into the equation and solve. So after I plugged in all of my numbers, I'm going to not read that again because I just did that over here. What I'm going to do is 2 things. First, I'm going to set this problem up where I actually do this the more complete version. I don't use the shortcut method that I did in the last video. The reason I do that is because I want you to see see how I actually deal with the units in this case. Because a lot of times, even when I was in chemistry myself, this constant right here, it kind of messed with my head a little bit in terms of how complex that constant was, at least in terms of the units. So a lot of times I would just say, I'm just gonna try and ignore the units, but I can't, because especially if I don't have all of this information all of this information here readily available, and I actually have to find certain things, especially if the problem gets a lot more complex, then knowing this constant and how it balances all the units in the equation is actually really, really helpful. So that's why I made sure to actually do this in the more complete version, so that so that you guys can see what is going on in here and what is and how the units actually get resolved, so that you know that you are getting the correct answer, and especially at least with the correct units. So here we go. First thing I do, and what I'm trying to do, I'm trying to move this units section over as slowly as I can, and I do that not because I want to make this any more drawn out than I have to, but I do this so that you guys can see how what I pull over to the left side of the equation becomes pretty much the opposite of what I've got left on the right side of the equation. So first off, I divide both sides of the equation by 234 moles because I'm trying to isolate my variable t, and in order to isolate the variable, I do the opposite operation that's being done to it. So it's being multiplied by 234 moles, so I divide by 234 moles on both sides of the equation. Now that I've done that, what I'm going to do now is I've got my number here, and I look over here and I see this really scary amount of units. And now, to be fair, I could have done the exact same thing and divided by 8.314 times cubic meters times kilopascal over moles per Kelvin. I could have done that. I really could have. But the reason I didn't was because then there would be this whole place where you could make a mistake, which is called fractions of a fraction. So I didn't want to actually deal with that just yet. So what I did was, in this case, I would say, well, I want to isolate this, but I don't like this two-lined variable, these two-lined units here. So what I'm going to do is in order to get rid of them, I'm going to multiply by the inverse. So which is the exact same thing as dividing by this and multiplying by the inverse of this are exactly the same thing. I just want to make sure to emphasize that one more time because it's always important to remember that those two things, they may sound different, but they're actually the same. So I want you to remember that. Use that to your advantage whenever you're working on these kinds of problems. So, invert this. So it's I'm going to multiply both sides of the equation by 1 over 8.314, and the units are going to be moles Kelvin over meters cubed per kilopascal. And why do I do that? Well, as you can see, I've got meters cubed in the numerator, meters cubed in the denominator. Meters cubed over meters cubed is still 1, just like kilopascals divided by kilopascals is still 1. So is moles divided by moles, and Kelvin divided by Kelvin. All of that comes out to 1. So of course I did that on the other side of the equation, and then I took this crazy number, and then using the reflexive property, I pushed this over to the right side of the equation. And now with my newly isolated t variable, I started going for it again. However, there was one problem in here, and that was there's pascals here, and there's kilopascals over here. And of course, kilo is the prefix for 1,000, so I would have to put like 1,000 in here somehow. And that's what I did, because as you can see, this is 8.314 over here, but when I wrote it again here, it's 8,314. I took away that decimal, or rather, I moved it over 3 places in order to change this from kilopascals to just to pascals. So I want to make sure that could, because those are some subtle, those are sometimes ways that problems can trick you. Sometimes they'll look at it and say, oh yeah, this is in pascals, but your gas constant is in kilopascals. So, if you don't do that conversion and you don't recognize that you have to do that conversion, you can get the answer wrong. And, that's something that you do want to consider, because that is something that's going to come up. And I'm sure a chemistry teacher in the future would definitely do something like that just to see if you're paying attention. So keep that in mind as we're going through this. So now I've got moles Kelvin over meters cubed per Pascal. I've got Pascal meters cubed over moles. So what we can start doing now is I can actually start merging the fractions together and get a nice number, which is 76 over 1,945,476. Try saying that 5 times fast. I'm just kidding, by the way. So you could start merging those numbers together, which is not hard. That's what calculators are for. But now let's take a look at the units. So I've got moles divided by moles, meters cubed divided by meters cubed, and pascals over pascals. And as we know, anything over something of the same value, as long as it's not 0, is 1. However, there is one unit here that cannot be canceled out, and that is Kelvin. And so this is where you kind of cross your fingers and hope that you're doing this correctly, because if this Kelvin is the unit that we need for the temperature, everything's good. But if not, you've done something seriously wrong in the previous steps, and you just got to go back and redo it. Fortunately, the unit for temperature is the Kelvin, so we are correct. All of these things cancel out, and we're left with our answer of 76 over 1,945,476 Kelvin. Now, do you have to change this into a decimal? You could, and that's not necessarily a bad thing, you know, and especially if let's say you're taking a multiple choice test and you were and they gave you answers that were in decimal places or in scientific notation, yes, you would have to convert it. However, if you were let's say you were doing let's say I gave you a test where you actually had to write down, or even for your homework, do you have to convert this into a scientific notation? The answer is no. You don't have to convert this into a decimal. You can just leave it like this. I would consider this far more accurate than anything you could do in scientific notation, because scientific notation always rounds the number. So don't worry about this. Just make sure that it is that your multiplication and division is correct and that this is the actual answer. But don't worry about changing it to scientific notation. The only reason you would have to ever really is because they don't give you this choice on a multiple choice test. So, you know, if you do, then you have to change it to scientific notation. That's fine. That's not a problem. But otherwise, if you want to leave it like this, at least for this homework assignment, feel free to do so. So that concludes this video on ideal gas laws, at least the example for that. Next time we'll go over some more of the gas law problems and how to solve those examples. So good luck in your studies. May the force be with you.